finally done. Alright, we need to celebrate.
Alright.
Try some of this Gatorade.
Okay. Hello?
Christian, where are you? Video project's due in 20 minutes, and you have the flash drive. Where are you?
What day is it?
It's Wednesday, Christian. Where are you?
Oh!
Good morning, Christian.
Not anymore!
There's no time!
God.
Search of gold made the nation bleed. They had lost their faith, and now they had to learn there was no place to return, nowhere they could turn.
I'm almost there!
So, we originally planned on doing our video project on building a Van de Graaff generator, but we couldn't build it. We had everything going, we had moving
Christian's
belts, and it just didn't work. It was mostly Chris's, mostly Will's fault. But, so, our new idea, go-karts.
So what we're going to do now is find the acceleration of my go-kart. First, we've measured time, displacement, and we know velocity initial is 0. So once we have the acceleration, then we can find the mass by weighing it, and we can also find the force at the bottom of the wheel by multiplying those together. Once we have the force, we'll have the distance from the lever arm, which will be the radius of the wheel, and that will give us our torque.
So, right here we're going to use a motion equation to find out the acceleration of the go-kart. And from the video that you've seen with Christian riding in the go-kart, we know that the V naught, or the V initial, is 0. And we calculated with meter sticks that the distance he traveled was 100 meters, and it took him 7.9 seconds. And we plugged that into our equation, and we got that acceleration equals 3.2 meters per second squared. After we found that, we used this to solve our force. We did F equals ma and plugged in our mass, which we found earlier, and the acceleration to find a force of 576 newtons.
53.8.
53.8 pounds.
$57.4.
57.4 pounds.
So we just add all these guys together, and then we have the weight of the go-kart?
Well, then we have to add Christian's.
Yeah.
70.8.
70.8 pounds.
Woo! Last one.
45.9 pounds.
Equally distributed.
Wait, can you redo that one? How is that 40? Oh, I guess the engine's over there.
Okay, weigh yourself, Fatso.
And with the helmet.
312 pounds.
Gearing up. Shane, can you please step out of the screen?
Oh, yes, please.
There you go.
Yes.
This is really good lighting. I like this natural light. Brings out the colors.
Still reading.
Christian, it's okay.
185.9 pounds.
Okay.
So right here we found the total weight, and the weight in the x is negligible because the theta is so small. Right here we have the wheel 1, wheel 2, wheel 3, wheel 4, and all the weights, and then the weight of Christian. And then we have our total weight right here.
On that note.
So this is just a quick explanation of what was happening while we were weighing our go-kart. So, because the scale obviously has a height, whatever wheel we were weighing was slightly higher than the others. This causes a slight angle between what we're weighing and where the rest of the cart sits. So, what we see here is, suppose this wheel is being weighed, it's slightly higher than the others, which is going to make the force of normal, which is the directly vertical line with the go-kart, is going to go slightly to the right, and there's going to be a small angle right there, which means that the force of weight is going to be only a component. The force of weight that we measured is only a component of what the true force of weight was. So here's a larger scale. This is the force of weight, this is the true force of weight, and that's going to be this hypotenuse, and the force of weight of the scale is what we measured, and then there's a small force of weight in the x going to the left, which is going to be what's going to change our calculation.
So we calculated the combined weight of Christian and the go-kart, and that came out to be 413.8 pounds. And we used a conversion factor of 0.453 kilograms to 1 pound, and we got the mass of Christian plus the go-kart to be 180 kilograms. Okay, torque equals force times the lever arm times sine of theta. This is how much force you're applying. The lever arm is the distance from the pivot point, and sine of theta, where theta is the angle between the lever arm and the force.
Okay, so now we're finding the torque of the wheel, and pretty much we're going to use the equation torque equals Fr sine theta. F is the force, and then R is the lever arm, and then sine of theta, which will equal out to 1 because theta is 90. The force required is 576 newtons, and the R is, what is it, Shane?
11.5 centimeters.
So 0.115 meters. Okay, so we're going to plug it into the equation here. And that equals 66.24 Newton meters.
So we just found the torque of this wheel, and since it is on the same axle as the sprocket here, we know that the torques are the same. And that torque is 66.25 Newton meters. Then to find the torque of the clutch here, we can use a ratio doing torque of the sprocket over teeth of the sprocket equals torque of the clutch over teeth of the clutch. And we got the teeth to be 58 and 13, which you can see the teeth here. And inside the engine you can see teeth if you want to get all in there. Doing cross multiplying, we get the torque of the clutch to equal 14.85 Newton meters.
Alright, so as we explained, torque is the force times the lever arm. And you may be thinking, well, how does that apply to me? How does that help me? Well, here's how. So imagine that you're riding a bike and you're already pedaling as hard as you can. So we're going to say that the force is constant. So we're putting a constant force on the pedals right here. And then we have our lever arm, which is also constant, except for thermal expansion, which we will neglect. So we then have a torque at a point. So at the first set of sprockets, you have a fixed torque because you're already pedaling as hard as you can, and the lever arm is fixed. So torque is constant. So now what we're going to look at is how you can change the force along the chain. So since torque's constant, you know that torque equals force times the lever arm. So what's happening is the force is going to be what's at the outside of the lever arm, right? So we have our point, and there's our lever arm is the radius, and the force is whatever's at that outside point. And that's going to end up being the change, so we'll always follow the outside of the sprocket. So what happens is, as we go smaller in lever arms, as lever arms go down, the force will go up because torque is constant. So when you're in gear 1, you have the most, you see the smallest gear, which is in back, you have the most force. And then on the outside, you have the least force. So as the lever arm goes up, the force goes down, and the opposite. Now in back, we have something different happening. So because the chain doesn't change, in the back the force is constant. Because we've set a gear here, we're pedaling at a constant, we're working our hardest already. The torque's constant up here, and the force along this chain is constant. Now, torque still equals force times lever arm. But now, the force is constant. So how is this going to change our torque? Again, as we said earlier, torque is the spinning force that acts at a point. So, over here, if torque is constant, as the lever arm goes up, the torque goes up. So the tall gears, the ones that you would use at high speeds, are the smallest ones. And the ones that you would use at low speeds, or when you're going up a hill, the ones where you require the most torque, is going to be the biggest ones. You can see here, the biggest one's the first one. And so, again, as the lever arm goes up, force is constant, the torque goes up. So the spinning power of the wheel is higher. And you may be thinking, why would you want less torque ever, or why would you want less force? Well, that's because you obviously want to have a higher top speed. So what's happening here is, when we go onto this outside big one, so we're back to the first one again, torque is constant, force is what's changing. So on this first one, we're going to have less force if we're on the biggest radius gear, which is this outside one. However, we're going to, with each pedal, pull more teeth of chain, because this has more teeth than the smaller ones, and therefore one rotation, if this is a 50-tooth chain, it pulls 50 teeth of chain. And so, as 50 teeth of chain are pulled, obviously 50 teeth are pulled on the other end too, because it's a loop. So as we go smaller in the gear sizes, one, we do lose the torque. So in the top gear, this is like a 10-tooth, we do not have as much torque as the first one, which is like a 40-tooth. But we have more velocity, because as 50 links of chain are pulled this way, if this one has 11 teeth and this one has 50, then it's going to rotate more with the 11 teeth, because 50 divided by 11 is a lot more than 50 divided by 40. Alright, so what we have here is, we're just going to show you two different examples of sort of the different extremes of the torque and force ratio. So right now we're on the smallest gear, which means that we have the most force along the chain. Up front, as I explained earlier. And then in back, we're on the biggest gear, so the one with the biggest lever arm, so we have the most torque in back. And now we're going to ask Stefan, you can just scoot back, we're going to ask Stefan to pedal, and I'm going to try and hold it back with all the torque that it has. And if you notice, I can't do it. If Stefan's pulling, he's not pushing that hard. However, I can feel quite a bit of torque. He's gaining on me. So now, so as you can see, with the force that Stefan applied, there is quite a bit of torque on the back wheel. Now this time, we have it the other way, so we have the least amount of force from the front because we have the longest lever arm sprocket up front, and we have the least amount of torque in the back because we have the smallest gear. So we have the least amount of torque. Now Stefan, try and pedal. I can stop it with my finger. So what that showed us is clearly with more force and more torque you have a more with our so what that showed us is with the big gear up front we can change our force, and the back gear we can change our torque. And so the more torque you have, the more spinning power you have. Now the reason why we have gears with smaller torque, because you'd think like, wouldn't you always want to have a max amount of torque? Well, the max torque isn't necessarily the max velocity. So before, if we spun the wheel once, the back wheel would only spin once. So we didn't have a huge mechanical, so we had a huge mechanical advantage. Now with this, if I spin the wheel once, the back wheel spins, I think that was about 5 times.
No, Christian, no!
Chris, you saved me! Sadness is tolerated when Mr. Willard's gone. See all the smiles in the class? I wonder why. Look at that. Wait, Mr. Willard came back in the room.
Wait. Okay.
Why are you Look at that. People just leaving. People leaving with free will. What? Oh my goodness. Is he standing before the bell? What? Look at that hood. Look at that hood. Look at that hood.
Captain, my captain.
Wow, look at all the danger in this classroom right now. We are just neglecting it. And look, there's Lizzie, just shocked by it all. And there's our substitutes. Say hi to Mr. Willard. It's a video for him. There are some people that stay productive. These are my friends.
Wait, Christian. There's no.
Okay.
No, wait. Don't finish it.
I'll see you tomorrow, Mr.
No,
Willard.
don't.
Oh.
So we definitely just got the cops called on us for driving go-karts around. So we're about to leave real fast. Oh, here's my ride. Let's go. Didn't we just get the cops called on us?
Yeah.
Yeah.
God damn it, Chris, come on.